Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 11.5, which is going to cover just kind of a short concept, and that is the concept of alternating series. Up to this point, we've really just talked about positive terms in series, and if we've had negative terms, the only instances have really been mainly where they're all negative. If all the terms are negative, then you can simply pull a negative in front of the summation and it becomes just the positive equivalent. But here, we're more going to be talking about what happens when the terms in a series, or its equivalent sequence, jump back and forth between positive and negative. What happens with those ones, and how can we determine convergence and divergence? We want to talk about these because some of the previous tests won't necessarily apply to those. A lot of the previous tests, for example, P-series and integral test, always needed to make sure that all terms were positive in order for the solutions to be true. However, for alternating series, it's a little bit different. Now, there's a proof for the alternating series on page 733 of your textbook, if you're so interested. And it kind of has to do with Newton's method of approximation, where you keep cutting closer and closer to its overall value, and that basically is what happens with alternating series, because we'll increase, but we'll decrease by less, and then we'll increase by less and decrease by less, and our goal is that we should be narrowing in on some place. But I have the results summarized here for alternating series, and this is everything you're going to need to know about it. Okay, so here we have for b sub n being greater than or equal to 0, we define alternating series as negative 1 to the n minus 1 times b sub n. That means that b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5, etc., etc. keeps alternating. Note specifically that we are isolating the values themselves of b sub n, and then we have what makes them negative separated from that. We have the negative 1 to the n minus 1. That's going to be important. Now, whether the first term is negative or the second term is negative or whatever you deal with, it's still alternating. You can always adjust this and change the exponents of this, and the concept still applies. So it could still apply if it's negative 1 to the n or negative 1 to the n plus 7. It still is the same concept, so don't worry too much about that. However, for the alternating series, we're going to be able to define if it's convergent, specifically if it's convergent, provided that the series follows these two conditions. If we satisfy these two conditions, then we can show it's convergent. First, we have number 1, which is that the following term of the sequence, so any following term is going to always be less than the previous one. And note that when I'm talking about b sub n plus 1 and b sub n, I'm just talking about the terms themselves. I'm not talking about them being positive or negative from each other. I'm just talking about the whole values, so the absolute value of each term. What this really means is that the sequence needs to be decreasing, or less strict, needs to be non-increasing. And that needs to be true for all n greater than or equal to capital N, which means after some point. After some point along the series, it is consistently either non-increasing or decreasing. It's okay for it to be non-increasing because if all the values stay the same at some point, then they're all going to be deleting each other eventually. So it should be okay. And then for number 2, we also want to make sure that the limit equals 0. If the limit specifically as n approaches infinity of b sub n equals 0, then we're all okay. If we have those two conditions, and then we are fine to show that something is convergent. Furthermore, the error made by using the partial sum s sub n is going to be equal to whatever the next term is. So if you use the first 5 terms, the error is going to be maximized as whatever the following term is going to be. And that is because we're going to then be increasing and decreasing by successive terms. So the next term is always going to be the next largest change, and then everything else is going to decrease from there. So if you have s sub n as the sum of the first n terms, then you need no more than the next term after that to indicate the error, which is actually going to be pretty easy for us to calculate. Now, one huge note that I want to point out that I already kind of talked about is that the textbook will say that this needs to be true for all n in this series, but that is not true. It only needs to be true after some point. The book is really trying to say that if you take out of first finite terms and then reset the series and maybe start it at 1, then it's okay to be true for all n. But you don't need that. As long as you need it for the infinite case, as long as you can show that it's decreasing for the infinite case and it's the limit is approaching 0 for the infinite case, then you're okay. We don't need it to be true for the finite case. If the first 100 terms are increasing, but then the infinite terms after that are decreasing, then you're fine. A finite amount of finite terms is not going to change whether the series is convergent or divergent. So it doesn't need to be true for all terms. We'll actually see a couple examples of this. Now, another note is that this test really only allows us to claim convergence for a test. Is not really helpful for showing divergence, which means if we failed either of these conditions or both of them, then we don't know if it diverges or converges. We just know it converges if these two things are true. If it fails these conditions, then we need to test something else. And typically what we're going to test is something like the ratio test in the next section. In terms of hierarchy, I usually recommend that you test this pretty quick. If you see something or recognize something as alternating series, go ahead and check the alternating series test to see if you can show that it is convergent from that. If not, then you could check something else. But this test is going to be relatively simple because all you need to show is that it's decreasing and the limit goes to 0. The limit goes to 0 is rather simple in most cases. You maybe need to use L'Hopital sometimes. And to show it's decreasing, you can either show that by directly proving it, by just plugging in what the n+1 term is and showing that that is less than the nth term. Or you can show it doing a derivative. The derivative is supposed to show where things increase and decrease. And if you can find the derivative and show that it decreases from some value up to infinity, then you're fine. So this is going to actually be a relatively simple thing to do. However, if you do happen to fail these, you need to keep in mind that you cannot use some of the previous tests, such as p-series and the integral test. You can use stuff like the nth term test to show divergence, but you can't use the p-series or the integral test because both of those are trying to use positive terms, and these include negative terms. So it does not apply. And we'll actually see how that is the case in the next example. For this example here, number 1, for the first 3, we're just going to determine whether they converge or diverge. Basically, if we can't show that it converges with the alternating series test, we'll need to show something else or try to show it diverges somewhere using something else. But here we have the summation from 1 to infinity of -1 to the n-1 over n. This should look familiar. If you did not have the top part here, what this really boils down to is the sum from n equals 1 to infinity of 1 over n. This is the harmonic series, which we know diverges. But that's not what we're dealing with. In this case, we don't have the harmonic series, we have the alternating harmonic series. And as I just talked about, the p-series test, which is what the harmonic series is, it's a form of a p-series, does not apply here. Because those are all positive terms. These are not all positive. These can sometimes be negative. So what do we do? Well, we're just going to do the alternating series test directly. We're going to try to show that both the terms are decreasing and that the limit is going to 0. Note, though, that in that test, that is working with the summation of -1 to the n-1 times b sub n from 1 to infinity. Which means, from this, if you separate out the -1 to the n-1, b sub n is only this 1 over n bit. The -1 to the n-1 is not going to be part of our evaluation when we show decreasing or when we show the limit. So do not include that part. Alright, first, decreasing, or not increasing, but decreasing is better. For decreasing, we want to show that b sub n plus 1 is less than or equal to b sub n. So we want to show that it's decreasing consistently. Now, to do that, okay, well, if we have that b sub n is equal to 1 over n, that's all we have here if we separate that out, then when we solve b sub n plus 1 less than or equal to b sub n, we just substitute directly. 1 over n for b sub n, and 1 over n plus 1 for b sub n plus 1. This, we already know, is true. The denominator on this side is going to be larger, therefore it's going to be a smaller number overall. So we already know this inequality is true. However, if you're not sure, you could always cross multiply on both sides, get n is less than or equal to n plus 1, which is still true. However you'd like to show it, but that's all it really takes. So that's the first condition. Then for the limit condition, we want to show that the limit of b sub n from n to infinity equals 0. Well, we're trying to do the limits as n approaches infinity of 1 over n. Well, that evaluates to 1 over infinity, which is 0. So we're good. So by the alternating series test, this converges. And that's it. That's all we need to show. Now that looked really simple, and this is a relatively simple summation to work with. However, what this shows, yet again, is that this is going to be different from P-series. The fact that you have an alternating series does make it different. We know that the harmonic series 1 over n diverges. We've proved that before. But with the alternating harmonic series, that one actually converges. So that's going to be your biggest example of the fact that some previous concepts from previous terms may not apply here. Okay. Generally, as a tip, if you're trying to show if you're trying to work with an alternating series up to this point, and you can't show that it converges with the alternating series test, try instead the nth term test. You may be able to show that with the nth term test that the series actually diverges. That tends to be your goal there. Okay, so determine whether the following series is convergent or divergent. This one we still have a summation, and we actually already have the negative 1 times k minus 1, or to the k minus 1 separated out. So we're going to take that out, and we're going to treat this k to the second power divided by 2k. We're going to treat that as our b sub k. Now we just need to evaluate both, again, we need to evaluate whether it's decreasing, and we also need to evaluate the limits. All right. Now, for this one, the limit isn't too bad. We can do the limit probably pretty quickly. You can do it in either order, whichever one you like. But looking at this, I see an algebraic on top, and I see an exponential on the bottom. I should know which of those wins, but for the sake of testing, we could always put this in. K squared over 2 to the k. Now, this one, the top goes to infinity, the bottom goes to infinity, and it's all about which one goes to infinity faster. And we can evaluate that by doing L'Hopital's on both the top and the bottom. Doing it once gives us limits of k to infinity. On top, we get 2k. On the bottom, we get natural log of 2 times 2 to the k. That still goes to infinity over infinity, so we can do it yet again. L'Hopital's. And we have the limits of k approaching infinity of 2 divided by natural log of 2 quantity squared, because I get another one of them, times 2 to the k. Now the only exponent, or the only variable here, k, is on the bottom, and that's 2 to the k. So this is going to approach 2 over infinity, which is 0. And that's all we need for the limit. So half of it's already done. Now for the other half, we need to show decreasing. Now again, you can do this by doing b sub k plus 1 less than b sub k. Or there's another way you can do it. You can instead consider the function according to this, which the function would be x squared over 2 to the x, and instead consider the derivative. If you find the derivative of this and determine where it is negative, that will show where it's decreasing. So the derivative of this one, it's not going to be the nicest one, but we'll see. So low d high minus high d low. So we have low times the derivative of high, which is 2x, minus high times the derivative of the bottom, which is natural log of 2 times 2 to the x. divided by the bottom squared, which is going to be 2 to the 2x. All right, with some manipulation, we see an x in both of these terms. I see a 2 to the x in both of these terms. We should be able to take those out. So x and 2 to the x in each of these. That leaves just 2 minus the single x left over in natural log of 2. So x times natural log of 2 over 2 to the 2x. And at this point, we're considering what happens as x is approaching infinity. So this stuff will always be positive, no matter what x is as x is approaching infinity. This will only be positive. So the only part of this that can possibly make it negative is this right here, the 2 minus x times natural log of 2. So we really just need to see what x values will make that term negative. So let's do that. On the side, I'll do 2 minus x natural log of 2. And to see where that's negative, we just simply make an equality for that being less than 0. Subtract 2 multiplied by a negative gets you x natural log of 2 is greater than 2. Divide by natural log of 2. X is greater than 2 divided by natural log of 2. And if you do that, 2 divided by natural log of 2 gives you 2.885. So x is greater than 2.9 approximately. Which means that this is negative for n for the terms greater than or equal to 3. Or I guess k we're dealing with. What this means is that x needs to be bigger than 2.9, and since we're just dealing with whole number terms, k equals 1, 2, 3, 4, up to infinity, this is showing that this is actually increasing for the first couple terms. That if you just plug in 1 and then 2, those are actually increasing up to 3. But after that point, it's going to be consistently decreasing. This is why I was saying you don't need to show that it's true for all terms in the series, just the infinite amount of terms. But that satisfies this condition, so yet again, by the alternating series test, this converges. Again, if the alternating series test fails, you can always try the nth term test or what we're going to cover in 11.6. Let's do one more example of the alternating series test. Determine whether the following series is convergent or divergent. Again, we're going to hopefully try to show that it is convergent. We have the sum of negative 1 to the n minus 1. Again, that's already separated out. Most of these will be. So we can keep that separate. Times natural log of n over square root of n. And this is going to be our b sub n. Okay. Now, to solve this, again, we have both of our pieces. I typically think the limit is easier, and you can go in either direction, so I'm going to first do the limit again. Usually the limit is easier, at least in my mind. The limits of natural log of n over square root of n as n approaches infinity. This is infinity over infinity, so we need to do something else because it's indeterminate. So like last time, we can simply solve this by doing L'Hopital's. If I do L'Hopital's on top, I'll get 1 over n. And on the bottom, I'll get 1 over 2 square roots of n. That simplifies to give us the limits as n approaches infinity of 2 root n over n, or the limits as n approaches infinity of 2 divided by root n. Two divided by root n is 2 over infinity as n approaches infinity. So this is 0. And that's all we need for the first part. Now for the second part, again, looking at this seems like it's going to be kind of hard if I try to do b sub n plus 1 less than or equal to b sub n. This really works for more simplistic things, kind of like what we did with the alternating harmonic earlier. A lot of times, it's better to treat this as a function and find the derivative of the function. So that's what I'm going to do. I'm going to take natural log of x divided by square root of x prime, take the derivative of this. Low d high, so square root of x times derivative of the top is 1 over x. Minus high d low, so natural log of x times the derivative of the bottom, which is 1 over 2 root x. Divided by the bottom squared, which is square root of x squared, which is x. This simplifies pretty nicely. Root x over x is 1 over root x minus natural log of 1 over 2 root x. So I should be able to pull out a root x out of each of those, or 1 over root x anyway. 1 over root x times 1 minus 1/2 natural log of 2, or natural log of x, divided by x, which is 1 minus 1/2 natural log of x over x to the 3/2. Now again, that's the derivative, and what we want to show or find is where this is negative. Well, as x approaches infinity or n approaches infinity, the bottom term will always be positive. Any positive term taken to the 3/2 will also be positive, but the top possibly could be negative. So that's what we need to focus on. So 1 minus 1/2 natural log of x less than 0. Subtract 1 multiplied by a negative, you get 1/2 natural log of x greater than 1. You get natural log of x is greater than 2. And then take e to both sides, you get x is greater than e to the second power. If you do e to the second power, you get about 7 something, right? 7.38. Which means that this is true after the 7.38 term or after n is greater than or equal to 8. So this is negative for all terms after the 8th one. And including. You could also say it's negative for n is greater than 7, or you could say negative is for n is greater than or equal to 8. Either one say the same thing. However you like to say it, we then have, by the alternating series test, this series converges because both of our situations were validated. Okay, so that's how you use alternating series test. What I also brought up with the alternating series is that you can also show where error happens. And error will happen when you try to find the term after some partial sum. What that means is really you just need to find at what point in the sequence would you need to stop adding terms to influence a certain decimal place. For example, here we have approximate the sum of the series correct to 4 decimal places. We have negative 1 to the n minus 1 over n to the 8th power. Now, this looks like an alternating series. However, if we're trying to find the sum of it, we first need to verify that it is convergent. And verifying this one is convergent takes very little time. Our b sub n is this right here, 1 over n to the 8th. So we have the limit of 1 over n to the 8th as n approaches infinity. That equals 0. That's good. That is true. Equals 1 over infinity. So that's true. And then for decreasing, we can actually do like what we did with the harmonic series earlier. 1 over n plus 1 to the 8th is less than or equal to 1 over n to the 8th. Well, this side is always slightly larger, so this is true. So, convergent by alternating series tests. Always good to confirm that before you just move on assuming that it's convergent. That way you know that you can use stuff like the alternating series test. Otherwise, you can do other ways of trying to find summation or rounding values. Now this says approximate the sum of the series correct to 4 decimal places. Now there's a few different ways to do this. One way is setting the function itself, 1 over n to the 8th, or I guess the sequence, less than some particular value. We have 4 decimal places, so I'd probably want to keep the first 4 decimal places as 0 to show that that I'm not influencing that any further. Or you can always just test values by plugging in values until you start seeing that successive terms aren't influencing the overall series anymore. Remember that the most amount of error will come from whatever the n+1th term is. So we just need to find where the term will stop influencing the fourth digit. A way that I can do that here, because we want 4 decimal places, I want to take 1 over n to the 8th, and I want to find at what point in the series will this value be less than something that influences the 4th decimal place. So I can say this less than 0.0000, that'd be 4 decimal places, so those aren't influenced. And if I don't want those to be rounded up or down at all, probably put 5 here. You can even put 1 as well if you want to evaluate that way, and you should probably get a similar answer. But this is showing that when you find 1 over n to the 8th, it's going to be less than 0.0005, which means the first 4 decimal places shouldn't be influenced. Evaluating this inequality takes very little time. Reciprocal both sides, you get n to the 8th is greater than this to the reciprocal is 20,000. Then you take the root 8 of both sides, so n is greater than the 8th root of 20,000. And the 8th root of 20,000, take 20,000 to the 1 divided by 8th power, you get 3.448. So n needs to be bigger than 3.448, which means n needs to be greater than or equal to 4. That means that at the 4th term and past it, all those terms will be less than 0.0005. So that means I really only need to add the first 3 terms to be correct to the first 4 decimal places. So I only need the first 3 terms. Therefore, I can plug that into my original series to find the sum. If I put in 1 into here, negative 1 to the 1 minus 1 is 0 over 1. So I start off with 1 over 1. And then I'm going to get minus and then a plus. If I plug in 2, I get 1 over 2 to the 8th. If I plug in 3, I get 1 over 3 to the 8th. The 4th term is where I'm going to start influencing less and less and less. But these first 3 terms should approximate the series overall to the first 4 decimal places. So if we do that, 1 minus 1 over 2 to the 8th power plus 1 over 3 to the 8th power. Just be careful of your minuses and pluses. You should get 0.99, and we want 4 decimal places, so 62. And that should be correct. If you even want to check, you can check to see what the 4th digit would be. That'd be the negative 1 over 4 to the 8th, or absolute value even. Just see what the 4th term would do. And if you do 1 divided by 4 to the 8th power, it's going to be 1.52 times 10 to the negative 5th. So this is about 0.000015. Meaning that even if I subtracted this away, it's not going to influence the first 4 decimal places at all. They're all going to stay the same. So that's one way of finding the first 4 decimal places, particularly if it's a series that's easy to solve, like 1 over n to the 8th, or at least it's easy to isolate n. If it's not that easy, like in this case, where we have negative 1 to the n minus 1 over n squared times 2 to the n, where I have n in a couple places that's really hard to isolate, you can simply just plug in values. However, first we need to check again that we can use this with the alternating series test. So we're going to do both the limit and show that it's decreasing. If we do the limit as n approaches infinity of 1 over n squared times 2 to the n, this is relatively obvious. You don't need to do L'Hopital's here. This is going to approach 1 over infinity, which is 0. So we're all good there. And then for decreasing, this one actually is not too bad to show directly. We can do 1 over n plus 1 to the second power times 2 to the n plus 1 is less than 1 over n squared to the n. If we cross multiply, so I get the powers of 2 over on this side, we have 2 to the n over 2 to the n plus 1 less than, and if I move the n plus 1 to this side, we get this, which is also just n plus 1 over n. And here we have 2 to the n over 2 to the n plus 1, which is really just 1 over 2. So we have 1/2 less than n plus 1 over n squared. Well, this is always going to be bigger than 1 for any value of n approaching infinity. So something bigger than 1 squared is always going to be bigger than 1/2. So this is always true for all n. So it is convergent by alternating series test. So that is true. Now we just need to find a true or the correct value up to 4 decimal places. In this situation, as I said, if it's hard to isolate n in just one place, then go ahead and try making s sub n. Go ahead and try making a partial sum. And what we're going to do is we're just going to start plugging in values until I start to see fractions that influence less than the 4th decimal place. So if I plug in 1, I get 1 over 1 squared times 2 to the 1 power, so that's 1/2. If I plug in 2, I get 2 squared, which is 4, times 2 to the second power, which is also 4. So I get 16 overall, subtracted. Then I get 3, so I get 9 times 8 is 72. Then I get 4, I get 16 times 16, which is 256. And then I do 5. Right, I'm on 5, right? Yeah, 5. So 25 times 32. 25 times 32, I think, is 800. 25 times 32 is 800, yep. And if I do one more, if I do 6 power, I get 36 times 2 to the 6 power is 64. So 36 times 64 is 2304. And we should start to see that 1 over 2,304, that is less than 1 over 1,000, which is 0.0001. So this is going to start to influence stuff less than the 4th decimal place. You can even check that. This term here, if you approximate that, will give you, technically negative, will give you negative 0.000434. Let's check. 1 divided by 2304 again. Yep, to the 4th decimal place, so 0.000434. So that's 4 decimal places, so maybe we can do one more then. If I do 7th power, I get 49 times 2 to the 7th power is 1 over 6272. Which tells e to the negative 4, so maybe one more just in case. 8th power will give you 8 squared times 2 to the 8th power. 16,384. That's definitely good. 16,384. All right. So these still might influence the 4th decimal place, so we keep those. But that's definitely going to be less. 1 divided by that number will give you, approximately 0.00006103. So that shouldn't start to influence it much, but we can always check. So if we put all these values together, we will get, with the 1 over 16,384 included, you get approximately 0.4484 if you round up because it's 39. And then this is 1, 2, 3, 4, 5, 6, 7, 8 terms. if you do the ninth one plus the error of 9, if you think about what the ninth term would be, this is 1 over, let's see, it'd be 9 to the second power times 9 times 2 to the ninth power, rather. Gives you 41,472. Which is about 0.000024. So that's definitely less than 0.005. So that'll definitely show when it's going to start influencing the fourth term less and less. So that should be the correct answer, rounded to 4 decimal places, about 4484. And you can even check this by going further by just adding the 9th, the 10th term, the 11th term. You'll start to see that these first 4 terms won't change anymore because you are always going to be staying around that same place. So that's another way to find it to some amount of decimal places, by simply just summing values until you stop seeing one term being influenced. But you should start to be able to recognize that by the fractions in terms of how big the denominator is, of like, okay, we're getting pretty close to where it's influencing. This one being 0.00006, 6 technically rounds up to 1, so this could be influencing the first 4 decimal places. But with the 9th term being 0.00002, that's probably not going to influence the 4th decimal because that doesn't round up at all. So we can keep it as that. All right, one of the first times we've actually been able to find sums of terms or sums of a series by actually manually doing it, and by also finding the error, which we kind of talked about last time with a different concept, but this one probably a little bit easier, less you need to do. Just find when the nth term stops influencing a certain decimal place. With that said, that's everything for this section for 11.5 for alternating series. Next time, we're going to be going into the last few different tests for convergence and divergence, and we'll have all the tests that we need, or that we'll have in this chapter, to address series. If you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. But with that said, I hope you have a nice day.